Here we go. All right. Last time you were here, if I gave you one word as to what did we talk about last time, what one word might you choose? What was the new thing?
Impulse.
Impulse. And what was the thing that we connected impulse to?
Grenade.
A what?
He said.
We can do better. If you apply an impulse to something, what does that become on the object? Well, impulse, the force concept is part of the impulse thing. What was my example for this?
Pushing on a shopping cart.
Pushing on a shopping cart. Where is the impulse in that example?
Push.
It's the push. Do you remember the two words that I talked about with the impulse and momentum?
Agent and agent object.
Agent and an object. And the agent is the thing that brings the impulse to the table, and the object is the thing that the impulse acts on, which in this case would be the cart. So the impulse part of that cart interaction is me pushing on the cart. What happens to the cart because I pushed on it? What is it now doing that it wasn't doing before? Come on. Okay, be more general than that. It's moving now, right? If it's moving, what does it have that this unit is about that it didn't have before?
Momentum.
It has momentum. Because what's the equation for momentum? Two simple things multiplied by each other? Mass times velocity. So when I walked up to the shopping cart, it was not moving, therefore it didn't have momentum. But after I interacted with it, now it's moving, which means it has momentum. And if somebody asked, well, where did that momentum come from? The fancy physics explanation is it came from the impulse that I provided on the cart. Okay? Now, let me get some examples here in case you're going, I hate the grocery store, I never go there. Okay? All right. I'm picking on Andreas because I know, and I know Connor bikes. Who else bikes? All bikers. What's the impulse momentum parallel to my shopping cart example?
You pedaling.
You pedal, and what happens, and what thing do you provide because you pedal? The fancy physics term.
Momentum.
No. Because when you pedal, what do?
You push.
You push on pedals. That's not momentum. But what is it that we talked about? One word.
Impulse.
That's the impulse. But what happens because of the impulse that you provide on the pedal?
You move forward.
You now have motion, that you didn't have before, which means what did that impulse become? Since you're moving now. M word?
Momentum.
You have momentum. Now, most people don't think of it in that picky of a term. They just kind of like, well, you pedal and then you move. But in the physics approach, the pedal is you provide impulse, and that idea that now you're moving, or maybe you move faster, that is a change in momentum. Okay? Let's see. Anybody soccer? We got no soccer people in here? Oh, damn it. Okay, what's the soccer application?
You kicking the ball.
You kick a ball. So what is it that you're kicking provides that we've just talked about? No.
An impulse.
That's the impulse, because you are the agent. What's the object?
The ball.
The ball. What happens to the ball because of your impulse?
Starts to roll.
It starts to roll, or if you provide a lot of impulse, it gets sent off. What does it now have that it didn't have before?
Momentum.
Anybody do lacrosse? Okay, if you do lacrosse, when you go to pass the ball, where's the impulse? It's in the stick, and you control the stick, and while you're moving it forward, there is your force times times the time, and it's not a super long time necessarily, but there is a time, and that impulse ends up being transmitted to the ball, which now has momentum being thrown off of the stick, either to go towards the goal or maybe a pass. Swimmers, where's the impulse? Actually, you could bring a couple things in here. Tell me, where does your impulse come from? What? Okay, and it's not just this. What else? What other body part are you using?
Your legs.
You're using your legs. So all of that becomes the concept of force that is acting over a time that ends up providing an impulse that becomes your motion moving through the water. So my favorite example, because I think it's simplistic, is the shopping cart. Okay, but you can apply this impulse momentum connection to a number of different areas. Okay, I know we got a rocket person in here. So when it comes to the rocket, where's the impulse come from?
The rocket engine.
The engine, and that impulse that most people would simplify by just calling it thrust ends up becoming the motion of the rocket, which means it has momentum that it didn't have before. So this impulse momentum connection is all over the place. So we have the big thing we talked about last time was this thing we called the impulse momentum theorem. Okay, and we summarized this in a math equation that looked like this. Okay? And the left side here was our impulse, and the right side was our momentum. Now, I gotta review one last thing. If we just talk about impulse, what technically was the unit that we get for impulse because it's force times time? We have newtons times seconds. What is the unit we get over here when we talk about momentum because it's mass times velocity? I'm going to do this in a different color. This was a big deal we talked about last time. What was the unit we got for because we take mass times velocity? Kilogram meters per second. What did we find out about these two things last time? Not just similar. They are exactly the same thing. And that is the main reason that we can set the two sides equal to each other. Even though this looks different, remember we went through that discussion where we said newtons is actually kilogram meters per second squared, but when you multiply that by this second cancels one of these, and what Newton seconds actually represents is exactly the same thing as momentum. And that is kind of the mathematical justification for why we get to set these two things equal to each other. Okay, so that's a quick recap from last time. So now what we're going to do is we are going to look at some of the problems, because our impulse momentum problems are number 7 through number 12 here. And so we are going to do a couple setups to hopefully help you go, oh, I get how to do this. All right. Now, let's start. I'm actually going to bypass 1 for the moment. I'm going to skip 7 and I'm going to go to number 8 first. So let's say we go look at number 8. So number 8 says, in 1992, Dan Bozich drove a go-kart at a speed of 78.4 miles per hour. Suppose he applies the brakes upon reaching this speed. If the combined mass of the go-kart and driver is 198 kilograms, the decelerating force is 361 newtons in the opposite direction, and the brakes are applied for 10.3 seconds. Calculate the final speed of the go-kart. Okay, so in reading that problem, somebody, if you're going, I don't even know where to start. What's the first thing you should at least do that shows you can start to break the problem down?
Show what is given to us.
Go through the identify what variables you've been given. So, can somebody, we're going to spread this around hopefully. Can somebody name one thing we've been given? Okay, Michael?
Initial velocity.
We have an initial velocity, and what is it that they give to us?
78.4 miles per hour.
Okay, now, at this moment saying that, are there any bells and whistles going off?
Yeah.
Okay, and why?
Because you need to switch it to meters per second.
Correct. So this, we're going to need to convert so we can get meters per second. So again, I'm gonna leave that to you. Somebody else, what else have we been given? Name a second thing. Okay, Julian?
The mass,
We've been given a mass, which is
198 kilograms.
198 kilograms. Do we need to worry about any conversion there? No, we want kilograms. All right, somebody else, can you identify another thing? Okay, Maria? Okay. Look at that. See, Maria hasn't even been here and she's already jumping in. The rest of you guys, suck it up. Good job. Okay. Anything else? There is one more thing. Alexis? Okay, so which variable would that be in this? It would be F, and what is it that they say about it? Okay, we get 361 newtons. If I said, can you give me a little more on this? Do you know what we would do? It would be negative because it really says it's decelerating, and it even emphasizes more by saying in the opposite direction. So that's negative. So let's take stock here. Here's our equation. We have a VI. We have an M. And that M is in two places. We have a T. And we've been given an F. So we do need to do this conversion, but once we have this conversion taken care of, then all we need to do is plug all the numbers in here and then treat it like a math equation and isolate and solve for the VF. Easy enough? Okay. Now I'm just double checking here. We had till 16. So before, I do not want to say, go ahead and do this one now. I want to go through one more and then send you off, giving you a couple extra that are kind of really straightforward like this, okay? So I'm going to leave this up here, but I'm going to choose another one and we're going to go through this. That one's pretty good. forward. Okay, all these are pretty straightforward. So let's see. Let's jump down to number 12. So I'm going to do this in a different color. No, I won't. I'm going to stick with blue here. And now we're going to do number 12. But I am going to write this same equation down. So if we look at number 12, it says the record for the smallest dog is a 113 gram terrier. Suppose this dog is running with a speed of 4.4 miles per hour when it sees a mouse and screeches to a halt in 0.81 seconds. What is the force required to do this? So, based on what they've given us, somebody tell me what a piece of information they gave us. Okay, Michael.
Mass is 113 grams, which needs to be converted to kilograms.
All right. Okay. What else? Okay, Stella.
Initial velocity is 1.4 miles per hour.
Okay. Anything you want to add to that? What's the unit?
Oh yeah, convert it.
Okay. What do we want to convert it to? Meters per second. Okay, so we got a little work on the side to do there. What else have they given us? Anybody? Anybody? Okay, Alexis? Okay, how much is it? Okay. And there's one last thing in there.
Final velocity is 0.
Correct. What's the key word there?
It's stopping.
Right. It says it sees the mouse. I think it says screeches to a halt. Okay? Which is language for it comes to a stop. So if we now come up to our equation, M, we do have to convert it, but we have the M. VI, they gave to us. T, they gave to us. And VF, they gave to us. So after we get all the converting taken care of, we just got to plug the values in and then solve for the F. Now you'll notice one thing about the answer. It has a negative sign. And that should make sense because if something's going to screech to a halt, the force has to be acting in the opposite direction. But I'm going to hold off on number 7. But on problems 8, 9, 10, 11, and 12, this way of approaching it, the way we did here, identifying, doing any conversions we need, and then checking off, what do we have and what are we supposed to solve for? I think this will pretty much work for you on all of the problems between 8 and 12. Okay? So your assignment is to work on those 5. All right? So what I'm going to do here, I'm going to change this and I'll make that 8. So you guys can work on these 5 problems, and tomorrow we might end up looking a little bit at number 7. But we're going to continue to talk about this impulse momentum theorem because there is I'll write these 2 words down. Let's see, what did I have? Oh, yeah. Tomorrow, if any of you have ever participated in something where somebody said, be sure and follow through as you like strike something, there's a reason associated with this why they're telling you to do that. And has anybody ever like thrown themselves onto the bed or onto anything soft, just like, and you're not worried about, oh, this is gonna hurt. It's just like, ah. Usually I'd say maybe like a bed that's really pillowy soft. There's a reason associated with this impulse momentum theorem that from the physics side of things explains why it's soft. So we'll have a discussion about these two guys tomorrow. Okay? Any final questions? No? Okay. Remember, if you're not here, what do? You watch the video.